Okay, so we are very happy to have Raghu today who will speak on the vacuum sphere and FZZT disk partition function in minimal string theory. So thanks again, Raghu, for coming, especially at such early time. And so you have 1 hour and a half, which you can split in as you want in discussions and presentation. Thanks, you can go.
Okay, thanks, Harold. Thanks for the invitation to speak at the String Field Theory Journal Club. I will be telling you about this paper we put on the archive last July with Douglas Stanford and Cynthia Yan, who is a graduate student at Stanford. And around the same time, there was related work that appeared by Dio Aninos and his group, which is in a slightly different limit, and they're motivated by de Sitter space, which we are not. But anyway, this the main technique is the same in their paper. Okay, so I will just begin by a quick motivation. So the sphere partition function without any operator insertion. So the worldsheet has the shape of a sphere. It's something that's the first thing you might think about is the most fundamental Feynman diagram, but it's a very confusing quantity. But it's interesting because there is an expectation that the value of this diagram should be equal to related to the on-shell value of the action of the string background. So in particular, it should scale like 1 over the string coupling square or the Newton's constant. So for example, in ADS 3 times S3, if you have a worldsheet, the sphere worldsheet should compute the central charge of the dual CFT, which is a quantity of order 1 over G Newton. Or if you have strings moving in a Schwarzschild background, hopefully it can compute the Bekenstein-Hawking entropy and things like that. So they're very interesting questions, but we don't know how to compute this quantity because there is a big puzzle that there is this unfixed conformal killing group on the sphere, PSL2C. And it has an infinite volume, it's non-compact, and also there is no way to regularize it to a finite value. And also the point is that until and unless your target space is non-compact, the sphere partition function you can solve is just 0. You can see that in many ways, but one of the points is that you have an infinity in the denominator of the path integral, which is the volume of this PSL2C. So you need at least some compensating infinity in the numerator to get a finite answer. And also typically black hole spacetimes and ADS3 spacetimes are non-compact. So you really need to deal with a non-compact target space in order to get an interesting answer. And this second paragraph is just a brief comment about some historic work. This paper by Liu and Polchinski, they showed that unlike PSL2C, this PSL2R, which would be the relevant conformal group for the vacuum disk partition function, has a finite regularized value. So it's something you can do. You can stick in the finite value and find some answers, but a more principled version of that calculation, you can do it in the superstring. So the super version of PSL2R is this group here. It's a super group, and that group has a finite volume. So what I'm trying to say is the disk is maybe slightly better behaved than the sphere, even though the bosonic version has some problems. Like it's not really clear in what sense you can replace the infinite volume by the finite regularized value. In the supersymmetric case, I think the situation is better because the group volume is just finite. Like the fermionic directions give a 0 and the bosonic directions give an infinity, and their product is well defined. And one can use this, for example, to give a direct path integral derivation of the de-Bruyn tension. I will mention this again in the end, but okay. So the problem is in the sphere is to divide by this volume of PSL2C. And
Raghu?
also there, yeah.
How is it for the group of the super closed string in the closed
It's
superstring?
also infinite. Yeah, it does not seem to have a finite regularized value.
Okay. Thanks.
Yeah, even though I have not computed those volumes, but there is a paper by Cyclin which claimed that, at least for the type 1 as a heterotic string. But there are two kinds of supergroup for the closed string. The one with just 1, 0 supersymmetry and the one with 1, 1 supersymmetry. But I have not seen the computations being done in detail. But
yeah, it does. I was looking at his paper and could not find easily the answer for the closed string, like indeed.
Yeah, but he mentions it in one place. But there are also old papers by Cyclin which claim that the sphere partition function should be related to the space-time action of the string theory, the space-time effective action. And I will also mention this in the end. So this, I'm just giving some general points. And one of the points is that in a non-compact space-time, like in the Schwarzschild black hole, the Gibbons-Hawking procedure, you usually have to put some kind of radial cutoff on the space-time. And you have to put some boundary term, this Gibbons-Hawking York boundary term, and there are some infinities that cancel, and then you take a limit and get a finite answer. So something like that seems not doable in string theory because it's like you're putting a cutoff in target space. So from the worldsheet point of view, it's a cutoff on field space. And that seems like a very unnatural thing to do. So this is another reason why it's kind of weird, because it's clear that the effects have to do with something to do with the boundary terms in non-compact spacetimes. And usually boundary terms are subtle, and so that's part of the problem. Okay, but we don't worry about all of that. We don't worry about critical string backgrounds. And as a possibly irrelevant warm-up, we compute the sphere partition function in non-critical string theory. And here the answer is completely well-defined, and it can be checked against the dual theory. The dual theory is just some matrix integral. So now I would like to just say a few words what this non-critical string theory is. So there is a Liouville sector, which does not decouple. There is a 2, p minimal model, which has a central charge less than 1 and actually less than 0, less than or equal to 0 in this case. And basically, we do the Liouville path integral directly in the limit when the Liouville central charge is plus infinity, which is the same as making P large. So C matter is going to minus infinity. And because the Liouville field is central charge is going to plus infinity, the path integral of the Liouville field can be done by saddle point. So this is the approximation in which the saddle point approximation is good for the Liouville sector. And there are some other methods to compute the answers, exact answers as a function of P. But since the point of this paper was more conceptual, we would like to just compute the path integral directly. We don't want to use some tricks involving the exact solutions of Liouville theory. We really just literally want to take the path integral and compute it. That's the philosophy. Okay, so a similar computation was done long time ago by Zamolodchikov in this paper on the entropy of random surfaces in 1982. But this was a short paper which had the main idea, but didn't compute all the numbers, like all the prefactors, like order 1 constants. So we go a little further and compute the one loop determinant. But I want to say that the basic idea of the calculation is already in this paper from 1982. And here is the main idea, is that because we have this Liouville field, and we are looking for saddle points of the Liouville field, that saddle point breaks the PSL2C symmetry. It means that if you take a saddle point and act on it with a PSL2C group, you generate new saddle points. So there's actually many, many saddle points. There's not just one saddle point. So the situation is that we are dividing by an infinite volume of PSL2C, but in the numerator, we have a non-compact family of saddle points, which also gives an infinity. And those two infinities cancel in a very precise way. because the saddle points are being generated by the action of the group in the denominator. So this is precisely the setting where a Faddeev Popov procedure can come in and help render the answer completely finite. So this thing in blue is really the main conceptual point that was there in this paper by Zamolodchikov, which is the existence of saddle points on which the conformal symmetry acts non-trivially. Usually in the bosonic string, in the critical string, the saddle point would be something like x of sigma 1, sigma 2 equals some constant x naught. And on this saddle point, the PSL2C symmetry just doesn't act. It preserves the saddle point. X naught stays at x naught. So that's why the Liouville field and the non-critical string theory helps us. And the second paragraph here is just supposed to say that because we want a precise match to the dual matrix integral, there are just some conventional subtleties like the conformal anomaly and the Euler character counter term in the string action. And there are some overall arbitrary constants in the sphere partition function. But those same constants also appear in the disk. So if you compute this ratio, sphere over disk squared, you get a precise number. You get a precise number is just some real number, and you can check against the matrix integral computation. Okay, so this is what we will do. So are there any questions about this main conceptual point? Is it clear? Okay, great. Okay, so then let's start by doing the Liouville computations. So I will not present the disk computations in detail because the conceptual steps are the same like in the sphere. But there are three components. So we have to identify the relevant saddle points and also the steepest descent contours through them. Then one has to compute the one loop determinants and finally treat this gauge group volume properly. So there are just the three steps. Just in any evaluation of an integral by saddle point, we do the first two steps, but because here we have a gauge symmetry, we have to do the step number 3 as well. So that's it. Like that's all we have to do, and we have to do these things carefully. Okay, so before we,
can I ask a question?
Yes,
yeah. So
yes, Ashok.
You will do the calculation in the large P limit, you said, right?
Exactly, yeah. Mm-hmm.
Yeah. So is there a systematic 1 over P expansion around this calculation?
Yeah, that one can also do. Yeah, actually, these papers by Aninos and Moolman do that. So that's just a loop expansion around that.
Okay.
So there will just be some.
In principle, you can get to any order in 1 over P. Is that right?
Exactly. Yeah, that's right.
Okay.
That would just be like the perturbation expansion of the Liouville sector.
I see. Okay.
Yeah, just loop diagrams in the Liouville theory.
Okay.
Yeah, thank you.
Okay, thank you.
Okay, so as I said, the main concept, one of the most important points is the existence of a non-compact manifold of saddle points. So that's in point number 1. And the origin of the saddle points, again to repeat, is the fact that the saddle point value of the Liouville field breaks the PSL2C symmetry. And that leads to 3 Goldstone modes for the sphere and 2 Goldstone modes for the disk. By Goldstone mode, I just mean the parameters parameterizing this saddle point manifold. So for example, on the sphere, the symmetry group is PSL2C, but actually a compact subgroup, a PSU2, is invariant. It leaves the saddle point invariant. So the Goldstone manifold, like in the usual symmetry breaking things, is like G mod H. So this would be like, on the sphere, it would be like PSL2C mod PSU2. And the PSU2 volume is finite, so that we can treat separately. The point is the integration over the saddle point manifolds cancels this, this volume of this coset. The volume of H is just finite. And the situation is the same, exactly the same for the disk, where the symmetry group is PSL2R, and a U1 subgroup leaves the saddle points invariant. So the coset manifold is a two-dimensional non-compact manifold, and its volume gets canceled by the saddle point manifold. Okay, and this is the second subtlety that I mentioned, that path integrals, when we usually compute CFT path integrals, there is a conformal anomaly that one has to be careful about. There is a term proportional to the Euler characteristic, which multiplies string coupling by a constant number. And also we have these PSL2R and PSL2C groups, and their volumes are well defined after you specify a measure on them. And one of the points is that the measures on the groups really come from the ghost fields. So you can't independently choose the measure on PSL2C and PSL2R. They're related in a very precise way. Just because you can only pick the measure on the ghost fields once. So the point is, if you compute this quantity in 1.1, so the CFT sphere path integral divided by PSL2C and the corresponding quantity for the disk squared, this 1.1 is a well-defined real number. And to deal with 1 and 2, what we did was, usually we think of the disk as having the flat metric, but one can equally think of it as the hemisphere, so half of a sphere. So that is what we do. We take the metric on the sphere to be a hemisphere, so it has Ricci scalar also positive. So then it's easy to deal with the conformal anomaly and things like that. Okay. So now, and this point I already mentioned, to determine the relative measures on the gauge groups PSL2R and PSL2C, you have to realize that those measures are really coming from the BC ghost zero modes and the measure on that field space. Okay, so all these factors are important, but they are sort of more technical. So now let's get into the details a little bit. So the Liouville field theory is the field theory of two-dimensional metrics, ds squared. And we parameterize like a reference metric, ds hat, times the Liouville field sigma, e to the 2 sigma. And we use this reference metric as the standard metric on the 2 sphere with the Ricci scalar 2. And if we were on the disk, the extrinsic curvature of the equator is 0. So you need these. And I would like to remind you that the Liouville central charge is usually written like 1 plus 6 times q square. And q is 1 over b plus b. And we take the limit of large C by taking b small. So in terms of that p parameter that I had before, b is square root of 2 over p. So p is large, b is small. So this will be the limit we will be working. So this is what the Liouville field means. And here is the action. So we just have a kinetic term that looks like a kinetic term for a scalar, but there is a coupling of the scalar to the background Ricci scalar and the cosmological constant term. This is sort of the only important thing. The other two lines are just some boundary terms with k, and also some order b to the 0 terms in the action, which you need to keep, because that's the accuracy to which we are working at. So notice that this is the parameter here, which makes the saddle point approximation well-defined, because there's an overall large coefficient in front of the action. B was small, 1 over b square is large. And this mu is the so-called cosmological constant, and mu b is the boundary cosmological constant. So this is the action. Now to find the saddle point, we can write the equation of motion. So we just do the sphere now. So I will write the action here. It was d sigma square plus r hat sigma plus 4 pi mu e to the 2 sigma. This was the action. And we try to look for solutions that are constant. And r hat was equal to 2. So this is 2 sigma. So it's easy, very easy to write down the equation of motion. It's just 2 plus 8 pi mu e to the 2 sigma equal to 0. And now you immediately notice a problem, that the metric was e to the 2 sigma times ds hat square. So there is no way that if e to the 2 sigma is positive, you can satisfy this equation because mu is positive. So actually, e to the 2 sigma has to be negative in this case for the solution to be found. And that's fine. So we just put e to the 2 sigma to be a negative number. And we find 2 sigma equals some log of 1 over 4 pi mu plus an imaginary shift by I pi times an odd integer. So e to the 2 sigma is negative. And that's okay because path integral, the integrand is a analytic function. So we are allowed to have complex saddle points. So in particular, this is a metric with a minus minus signature. The physical metric has minus minus signature. And that is why you can actually satisfy the Liouville equations of motion, because remember that the classical Liouville equation just says that the Ricci scalar has to be -2. And this metric minus d theta square plus sine square theta d phi square, its Ricci scalar is -2, not +2. So that's sort of the message. And and also notice that there are actually an infinite number of solutions labeled by this n. So it's not just one saddle, you find some infinite number of saddles. So now we just take these values for sigma and plug it into the action, which we had here, and I also wrote here. And you just compute the value of the classical action. So you notice that there are some exponentials of 1 over b squareds that you expect from a semi-classical thing, but also there is a phase factor. This e to the minus I pi over b square 1 plus 2n. So the action depends on n, this n labeling the saddle point through this phase factor. Okay, so this fact also I already explained, that this e to the 2 sigma ds hat square has to have constant negative curvature, and the way it achieves that is that it's a sphere with a minus minus metric on it. And they count as valid complex solutions to the equations of motion. And there was related discussion in a paper of Maldacena, Turiachi, and Zhang in the context of de Sitter JT gravity. Okay, so now
okay.
I
have one more question. Yeah. So, I mean, presumably this Liouville of central charge infinity is accompanied by some other theory, right? Because to make the total central charge
right,
correct.
this is the matter. Yeah, right.
Yeah, the matter. So far, you have not said anything about the matter, right?
Right. Yeah.
And
so
that will play some. I'm just wondering, because once you have broken this PSL2R, I mean, you have solved that problem, then it's automatically solved for the matter sector also, right? There is, you don't have to divide. I mean, there's only one PSL to divide by.
Exactly, yeah. So how it works for the matter is that for the matter, the sphere over disk squared is just finite by itself.
But that presumably depends on what boundary condition you put on the disk, right? Because disk is more like a
right. So we worked with the boundary condition that it corresponds to the Cardy state with where only the identity, propagates in the cylinder. So the answer that matches to the matrix integral is using that specific Cardy state for the matter sector on the disk.
I see.
Yeah.
And the matter sector in principle could consider include a Schwarzschild black hole solution. Is that right?
In principle, yes, but in the paper we were focusing on just the minimal models, thinking of the minimal model, because we wanted to match to the matrix.
Okay, I see.
So far it has not entered. Yeah, right.
Okay, but in principle you can apply it now to any matter system, right?
Yeah.
As long as the total central charge is minus infinity.
Yeah, is going to minus infinity. Yeah.
Okay.
Right.
Okay, thank you.
Okay. Okay, so now there is a next step, which is which of these n's are we supposed to sum over? And the answer is that we have to sum over half the n's from like 0, 1, 2, etc. And I will explain that on the next slide. But the point is, now when you add up these phases that I had, e to the I pi over b square 1 plus 2n, they give you the 1 over sine, 1 over sine pi over b square. Just the geometric series resums into this. And for people who are familiar with the, if people are familiar with the Liouville formulas, there's always these 1 over sine pi over b square around. And this is how it comes. It comes from this infinite sum over n. Now, I first should have multiplied here the one loop factor and then did the sum. But what it turns out is that the one loop factor is independent of n. So I can do this. And when we compute the one loop factor, we'll just see that it doesn't depend on n. So we just multiply this whole expression 1.5 by the one loop factor. Okay, so what is going on in this one loop? So why are we summing over only half of the saddles? So to motivate that, consider this toy integral. So integral d sigma e to the a sigma minus e to the 2 sigma. So this is a toy model for the zero mode of the Liouville sector. So the actual action is d sigma square plus r hat sigma plus mu e to the 2 sigma, right? And it's the exponential of minus that thing. So we drop the d sigma square because we focus on the zero mode, the constant mode. So you see that we have an integral of this form where little a is negative. Okay, so this is the integral we want to do. Now note that as sigma goes to plus infinity, the e to the minus 2 sigma makes the integrand convergent because there's just an e to the plus 2 sigma here. It's very big, so it's e to the minus that, so the integrand is convergent. On the other hand, for sigma goes to minus infinity, we have a problem because a is negative. If a was positive, it would be okay. Because this e to the 2 sigma drops out in that limit, and the integrand looks like e to the a sigma, which is e to the plus infinity now because a was negative. So we need to do something. We need to define this integral somehow. And the point is we can define it by analytic continuation. So if you start from the positive a, where the integral is well defined, and make a path in the complex a plane, let's say through the upper half plane or the negative half plane, then an acceptable definition of the contour is the following. So this is the complex sigma plane, and this is the defining contour here, the black thing on which I put the arrow. So if you take this contour for positive a, you will get the answer you wanted, and it would be well defined for all a in the upper half plane. And these black dots are now the saddle points that I wrote with the imaginary shifts in I times 1 plus 2n. And these dotted lines are the steepest descent contours. So you see that you can take the defining contour and you can just like wrap it like this through all of these guys. So that is why you only sum over like n equals 0, 1, 2, 3, etc. And these lower ones don't count. They don't fall on the contour when you deform it. And this might seem surprising, but I want to say that it's not that surprising, because let's make a variable change in this integral, which is e to the 2 sigma equals t. So then we get an integral from 0 to infinity dt over 2t t to the a over 2 e to the negative t, right? This is just a gamma function integral. It's like gamma of a over 2 plus 1. but with A is negative. And what we are trying to do is trying to get asymptotics of gamma of A when A is negative infinity. Now, the usual Stirling approximation doesn't work in this case, because to get the asymptotics for gamma of A when A goes to minus infinity, you need to use this rule, gamma of 1 minus A, gamma A equals pi over sine pi A. And you need to use the Stirling approximation on this guy, because this is gamma of a big positive number. So you see that the asymptotics of gamma of A has this 1 over sine in it. So essentially what this procedure here is doing is giving the asymptotics of gamma of A when A is minus infinity without using this reflection formula. So you can see it's like a sort of a first principles derivation of asymptotics of gamma A when A is negative infinity. So you can think of it that way, and then this sine of pi A factor is not mysterious. And A was precisely this 1 over B square. So it's like sine pi over B square. Anyway, these are all some cute mathematics you can do in this thing, but the point is there were some saddle points and we summed over a bunch of them. Now, just to flash quickly, the disk is a similar, there is an equation of motion. Now the sigma is not constant, but it depends on theta. There is a boundary condition, and you have some explicit solution with again some shifts in 2 pi I n. And this alpha parameter appears here in the solution, and the boundary condition relates alpha to mu b. And we were only able to compute the one loop determinant in the limit that alpha is small and positive. So this is the limit that we took, and it was enough for us, because really the purpose of the disk was to go in the denominator of the sphere square. So anyway, you can play the same game. You can compute the on-shell action. You can sum over half the ends, find this factor, sum it over, get a sign. Everything is the same for the disk. There's no subtlety anymore. The only point is that the answers depend on this extra parameter alpha, which depends on the boundary cosmological constant. Anyway, so now we come, okay, are there any questions about this before we go to the step 2, which is computing the one loop determinants? Okay, so let me go on. So it's the standard technique. How we compute one loop determinants is we write sigma as the classical field plus a fluctuation. And we want to do the integral over chi with a Gaussian weight. And if we make the expansion of the Liouville to higher powers of chi, this will generate the series that Ashok was asking about in his first question. So if we keep chi cubed, chi to the 4th terms, we would generate the 1 over p series. But we only keep chi square terms. So first, we need to define a measure on the chi space, and we do that by defining a metric on the chi space. So there is this arbitrary constant capital C that enters there. Okay, so that's just a metric. And this parentheses is an inner product, which is defined by taking the two functions and integrating them on the reference metric sphere. Reference sphere. Okay, now here is the point. So when you take the Liouville action and you expand to quadratic order in chi, you find this partial chi square minus 2 chi square. That's what you find. And okay, the spectrum of this. So how do we compute the determinant now? So essentially this path integral is a determinant 1 over square root of del square minus del square minus 2. And we just know the eigenvalues. This is just the Laplacian on the sphere minus 2. So the eigenvalues are LL plus 1 minus 2. They have a degeneracy 2L plus 1. Okay, now notice that L equals 0 is a negative eigenvalue, and L equal to 1 is 3 zero modes. So what are these? So let's first understand these. The negative mode is really the fact that the steepest descent contour in these things is going vertically through the saddle points. So L equal to 0 mode is constant on the sphere. So this is precisely what we were discussing in this diagram. And notice that the directions here are vertical, right? So that gives some I in the path integral. When you do the integral, you get some I. So that's what the L equal to 0 negative mode means. The 0 modes are precisely this Goldstone manifold. So if you sit at a saddle point and add a little bit of the L equals 1 mode, that's like a new saddle point, which has the same action as before. So you see here very explicitly that these 3 Goldstone modes that I was talking about are nothing but the L equals 1 modes on the sphere, and they have 0 action. So they lead to an infinity in the path integral, which cancels the infinity of the gauge. Okay, so this equation 1.15 is what I was trying to explain before about the 0 mode and the factor of I. So we have a 0 mode, so the exponential looks like e to the positive, but we are supposed to integrate in the vertical direction. So it's actually a convergent integral, and we have an I here from just d chi being proportional to I. Okay, so that's it. So, and the 0 modes, we deal with them by the Faddeev-Popov gauge fixing. That just means we're not really supposed to integrate over them. So we just put a delta function for those and deal with them later when we do the step 3 of fixing the gauge group. Okay, so that's about L equals 0 and L equals 1. What about the higher L's? That's some standard computation. So we are supposed to compute a determinant. This is the expression for the infinite product from L equals 2 to infinity, 2 to infinity. And there's just some standard zeta function way of doing this. So this product naively would just be 0 if you computed it, because there's some very big factors in the denominator. But you can regulate this and get a finite answer. All this is pretty standard for computing things using the heat kernel and stuff like that. So in particular, one needs equalities like this. So if you have a sum over 2L plus 1, you suppress it using the eigenvalue, and you get things like get a divergent piece, which you're supposed to drop, and you get a constant piece. And similarly, this other thing. I would like to add that the second sum we could not do analytically. I mean, there's possibly some expression for it, but we were happy to just compute this number numerically by first analytically identifying the divergent terms and then doing the sum numerically, subtracting those off. But in principle, there is an analytic expression for this number, which in our paper we didn't find. So anyway, so that's it. So, and then there's a similar thing you have to do for the disk. This is the quadratic action for the chi. There's an eigenvalue equation. There's a boundary condition, so on and so forth. Anyway, it's exactly the same. It doesn't matter. So I'm just going to skip over all of these things. And we come to the step 3. So was there any question about this one loop, the one loop computation of the one loop factor?
I had a small question, which is that, so ultimately you will be comparing it to the matrix model, right?
Yeah. Mm-hmm.
So that doesn't fix this constant? The numerical constant? The numerical constant that you showed?
Yeah. Well, there's also similar constants in the disk we didn't compute, like this one.
I see. So the ratio is somehow fixed, or the difference is has an analytic expression. Right?
Yeah, exactly. Yeah.
Yes.
Exactly. Mm-hmm.
No, thank you.
Yeah, there are a bunch of these numbers that we just computed numerically, like even in this equation, there is this. Okay, so now we have to divide by the volume of this group, and this point I have already said many times. So let's come here. So in the numerator we have this d chi1, d chi2, d chi3 integral, and in the denominator PSL2C has dimension 6. So we call these directions S1, S2, S3, and B1, B2, B3. And S1, S2, S3 generate an SU2. So this volume is just finite, integrating over S1, S2, S3. And the chi and the B, you can think of them as you can do a change of variables from chi to B. And the only point about this determinant is that you have to compute it carefully. It's some order 1 thing, like it has 2's and pi's and log 4's in it. So one has to be careful about the order 1 factor, but this is a finite determinant. That's the point. And for the disk is very similar. Like you have 2 zero modes, chi1, chi2. In the denominator, you have a U1 and this coset, and there is a determinant. Okay, so let me now discuss what is this conformal symmetry and how is it broken. So it's equivalent to work with the ZZ bar coordinates on the reference sphere like this. So we have the metric 4 over 1 plus ZZ bar square. And one has to remember that the Liouville field does not transform like a scalar. What you're really supposed to do is that this combination is supposed to transform like the metric. So what that means is when you do a coordinate transformation on the Z, the sigma changes. In principle, it changes. So you have to write something like this equals e to the 2 sigma tilde ds hat tilde squared, where the tilde means a change of coordinates from Z to Z tilde. Okay, so here are the explicit vector fields that generate those infinitesimal conformal transformations. So there are 6 of them. So for example, this first one, Z goes to Z plus I epsilon Z is just a rotation, right? This is just Z times e to the I epsilon. And we see that this rotation of Z by a phase leaves the ds hat invariant. So 1.25 is invariant because it's Z times Z bar. So rotation by Z is one of the SU2. Rotation of Z by a phase is one of the SU2 directions. So that's like S. S means symmetric. On the other hand, if you look at number 4, it's like Z goes to Z plus epsilon Z with epsilon real. So the finite version of that is Z goes to e to the epsilon. So it's a real rescaling of Z. And then the sphere, this background metric is not invariant under that. So the sigma has to soak up that non-invariant so that this equation at the top of the page can be correct. So the sigma transforms under 4. So this is a broken generator. And similarly, you can fill out this table. Now, the point is that on the disk, only the first 3 make sense because they are the ones that preserve the hemisphere. The other ones, like this rescaling of Z, shift the equator. So the ones that are relevant for the sphere are the top 3 guys. What time is it, by the way? Okay, so I would like to maybe go for another 10 minutes and then we can have just an open discussion. I'm almost done. So the last step is to figure out the precise relation between the coefficients of the chi's and these fields. And that you do by putting a metric on these vector fields, right? So as I was saying, these holomorphic vector fields are the BC goes 0 modes. And to define the measure, you have to define a metric on the space of these vector fields or the space of the 0 mode. This 3 over 8 pi is just a convention. One can delete it, it doesn't matter. But the point is for the disk and the sphere, it's integrated over the disk or the sphere. So you get different normalizations. This MAB is different for the sphere and the disk. So you have to take that into account. Okay. So here is even more explicit. This equation 129 is what I wrote before, that how sigma tilde is related to sigma. So if you work out for the 6 transformations I wrote, you have these 3 invariances, and the other 3 generators generate shifts of sigma of this form. And people who have experience with this thing would be able to realize these 3 as the 3 spherical harmonics with L equals 1. So like Z plus Z bar is related to X, and Z minus Z bar is related to Y, and so on. So anyway, the point is, we had this other metric on the sigma space, which we defined by saying it was C square, d chi d chi. So what enters in this determinant of chi over B is the ratio of this metric on the sigma space to this metric on the ghost space. Okay, so one has to compute that. And once you take those 2 metrics into account, you find these 2 determinants in 132. So for the sphere, you find some 1 over 3 to the 3 halves. And for the disk, you find this log 4 minus 1 over 4. Okay. So let me just give you the final answer here. So here is the final answer on the top. I didn't discuss the disk much, so we can just focus on the sphere. So this first parentheses is the sum over the on-shell action for the saddles with different n. There is the 1 over sine, which came from the sum over n. The second parentheses is the 1 loop factor. The first factor is L equal to 0 modes, the L equals 1 modes, and the higher L modes with this numerical constant here. And finally, this last piece is coming from the volume of SU2 and that Faddeev Popov determinant between the chi and the B. And very similarly for the disk, where we have these 2 more numerical constants in here. So this is sort of the main result of the paper, is to compute these integrals. And notice that this capital C is pretty much arbitrary. And there's also a mu and an alpha in these formulas. But then when you take the ratio, you get something much nicer. That's okay. And then, like what Ashok was saying, we also have the matter sector. We should not forget about it. So on the disk, we put the boundary condition that it's this the identity Cardi state. And there is just a formula for the sphere over disk squared for that. So then you multiply the answer that, and basically you get a very simple answer. This is only in the large P limit. So you just get P times this alpha to the P plus 2. Alpha, remember, was related to mu B with the boundary cosmological constant. Okay, so this 1.36 is what you should match to the matrix. And it does match. If one has to understand how to compute the sphere, how to compute the disk, and yeah. So are there any questions about this before I just in 5 minutes say what the matrix computations are?
I just wanted to know what was the ratio of that the constants turned out to be. I mean, you had those unknown constants.
Yeah, one can work it out from these explicit formulas. We haven't, I haven't written it. Yeah.
So it's made up log cell 2. Okay.
Yeah, it has this log 4 and some 2s and pi's in it. That's the only thing.
Okay. Okay.
And maybe this 3 to the 3 halves and so on.
I see. Okay. Thank you.
Yeah, thanks, Ashok. Yeah. And okay, so let me just say how one computes the sphere and so on. So the sphere partition function is literally just doing the matrix integral. So these minimal string theories have a dual description in terms of an integral over a matrices, e to the minus n times trace of some potential. Okay, and you just have to compute. So this is z, and the log of z is the free energy, and the sphere term is just the leading term in this. So there are many techniques in the matrix literature to compute this. And there is also this disk partition function that we computed is related to the following expectation value. It's like the log of the characteristic polynomial of the matrix. So the characteristic polynomial is determinant of x minus the matrix. So it's just the log of that. And this x here is related to alpha. So you see that the FZZT quantity has a free parameter in it, which is x is just the boundary cosmological constant. And again, it has a 1/L expansion, and the disk is the leading term, is the leading large L term, which, because this trace is given by integral d lambda rho lambda, is equal to this thing. And just one can compute these things. And let me not go into the subtleties and so on, but the point is one has to input something. So this matrix integral, this potential is arbitrary. So you have to pick a potential in order to match it. And there are known ways of picking this potential in order to match to the string theory computation that I presented. And one of the results in that literature is that you have to tune the potential so that the density of states looks like this. It's some sinh of arc cosh of 1 + 2 times the energy. So one has to fine tune the potential so that you land on this density of states. And this epsilon here has to do with the so-called double scaling limit. So the matrix integrals that are dual to this string theory are not just matrix integrals in the 1/L expansion, but you also have to take an additional limit on top of that. And this epsilon is a parameter that appears there. So anyway, the point is there's a bunch of details, but in the end, you know, when you compute the answers, you find a precise match. So let me just present the final answer. Is here in this equation 2.12. And this is a precise result as a function of p, but taking this limit. So you see this factor is 1, and you have this 1 times, well, here it's 1 times p times alpha to the p + 2. So it matches. So this is like a strong check of the fact that if one really has access to, you know, getting rid of this volume of PSL2C somehow, then the answers really do make sense, like in a very precise way. So anyway, that was the main part of my talk. So maybe I would like to conclude there and take some questions before maybe going on to the discussion part of the talk, which are just some vague comments based on what Harold asked me to say a couple of words about some papers. Okay, thank you.
Thanks a lot, Raghu, for the talk. So do we have any question on this part of the talk? So I will start with a small one. So I think it's related to what Ashok. So this 1.00, it's like when you combine all the numerical values you got before, like it just becomes 1 up to a few digits, right? Okay.
Yeah, exactly. Yeah. I mean, we are just not good with the zeta function determinant. Otherwise, one can maybe have.
It is that it just conspire to get 1 at the end. And
yeah, we didn't expect the answer to be simplified in the end because it was just some numerical constants, but they happen to be this thing. Yeah. Anyway, so let me, if there are then no more questions, maybe I can make some comments about this. One is just a comment about some unpublished computations that we did, and also some the same computation appeared in this Eberhard-Pahl paper, which is the fact that for the super version of the conformal group on the open string, which has 3 bosonic generators, and 2 fermionic generators. The volume of the PSL2R, or the super version of it, is finite. And one can use this to compute the tension of a DP brane. So this would just be the disk partition function with the Neumann and Dirichlet boundary condition appropriate to the P, the value of P, divided by this volume, which is some like negative pi square or something. It's just some finite number. This you might think is a little bit funny, maybe even in the supersymmetric case, it's a little bit funny. But what I can say is that there is this recursion relation between a DP brane and a DP minus 1 brane between their tensions. And that is just Z of a scalar field with Dirichlet boundary conditions on the disk, and the same partition function with a Neumann boundary condition. Because when you go from DP to DP minus 1, there is one scalar on the worldsheet whose boundary condition you are changing. And this is just 1 over 2 pi. This ratio is completely unambiguous. So that's just like one comment. It's like a clean thing that's, I think, completely uncontroversial, the second comment. The second vague comment has to do with this paper's.
You are saying that
yes.
this, not just the ratio, but the actual TP comes out correct by this?
Yeah, that's the first paragraph that I'm saying. Yeah.
Okay.
Yeah, if we input this minus pi, well, again, I was a little bit quick about this. The tension comes out correct in units of, let's say, the low energy Newton's constant. Yeah. So one has to fix that somehow, but once you do that, then it comes out exactly right.
Okay. Yeah, I mean, for that you have to go to sphere 3-point function, presumably.
Right.
I mean, if write the Newton's constant in terms of string tension. Yeah.
Exactly. Okay. Exactly. So we took a bunch of those formulas from this the second volume of Polchinski, where he relates the kappa appearing in the low energy action to, let's say, the graviton 3-point amplitude. And so we took it from there.
And you are saying this cannot be done for bosonic string. Is that right?
Right. So for the bosonic string, well, Liu and Polchinski did it, but the issue there is that the PSL2R volume is really infinite. So setting it to a finite value by hand is a little bit fishy, I think.
I see. Okay.
Yeah, the difference is that in the super version, these two fermions in a precise way cancel the infinity coming from the non-compact bosonic directions.
Okay, yeah.
Yeah, so there, this denominator is really finite.
I see, okay.
Yeah. Okay, yeah. And there are some papers by Cyclin, for example, this paper. It's a partition function of the sigma model of the string on a compact, I don't know. I never understand these papers. So please take this next comments with a grain of salt. The main idea is the following. So first, let's not imagine a complicated sigma model. Let's just imagine a CFT, just like a free scalar or a WZW model or minimal model. The sphere partition function computed at two different radii, R1 and R0, satisfies this condition. This is just the statement of the conformal anomaly. You might have thought that it's a CFT, so the partition function should be independent of radius, but it's not. It depends on this radius in a very simple way, R1 over R0 to the C over 3. So what Cyclin wants to do is now take the string sigma model, separate the worldsheet fields into 0 modes and non-zero modes. So 0 mode means x mu, which is independent of sigma 1 and sigma 2. So you write x mu of sigma 1, sigma 2 as a 0 mode plus a function of sigma 1, sigma 2. Okay. And he says, do the integral over the non-zero modes. So keep the 0 modes fixed, do the integral over the non-zero modes on the sphere. So you get a function of the 0 modes, right? Because the 0 modes were fixed. And his claim is that when you do the integral, you get a central charge functional. So just like here, right, the sphere partition function is related to the central charge. So he is saying that if you were to fix the zero modes, do the integral over the non-zero modes, the answer, the analog of C, is a central charge functional which depends on the sigma model couplings like G mu nu of X, B mu nu of X, and phi of X. And further, his claim is that this should vanish, right? So on shell, if the sigma model was conformal, really conformal, the central charge will vanish. And he uses that to say that this function 3.2 that you get is also the action density in the space-time effective action. Like it would be Ricci scalar built out of G plus H square plus grad phi square and so on. So this is the main claim. And kind of a naive check of this is that on shell, the central charge has to vanish because of conformality. But also we know that the bulk term of the on shell action vanishes, right? Because this is a fact which was, for example, explained in this recent paper of Maldacena, Witten, and Chen. In one of the sections, they explained this. So this is the message of this paper. These papers are short. Some of them don't have all the details. So I don't know how correct it is, or yeah, but this is, I think, the message. There must be some truth to it, but at least the literature is kind of hard to penetrate on this point. At least was this thing clear that I tried to convey, or? But yeah, I don't know. So in particular, this is like related to the beta function of the dilaton, or some linear combination of the dilaton and the trace of the graviton, or something like that. That's also the claim, that one particular beta function comes out by just doing the sphere path integral.
So I have a question here.
Yeah.
So when you say action density, does it contain square root of minus G, or does it not?
Yeah, my comment was much more primitive. I think that kind of detail I don't know.
Okay.
Yeah, I would presume what they get is a linearized action. Like, so you have to expand G as eta plus H. And at least in that limit, it doesn't matter, I think in that limit, they should get the whole thing, right? With the square root of G expanded as 1 plus H.
Okay.
So, yeah. As I said, it's not perfectly clear to me. Yeah, anyway. But at least this seems to be the claim, right? We can read here. Special attention is paid to a proper separation of the path integral into the integrals over the constant and non-constant parts of the coordinates. And they're talking about a C theorem and a partial derivative of Z over the logarithm of the cutoff, which is the beta function. So anyway, and the final comment, which has now come up in discussions both with the Eberhard Paul and also with Ashok when I was discussing with him earlier this year, is that a more universal approach seems to be the following, that the dilaton zero mode is a universal operator that appears in all string theories. And I don't understand this very well yet, but it also has an expression in terms of just the ghosts. There's a ghost fields like C1, C-1, and so on. So the idea would be to first, let's say, compute the third derivative of the sphere with respect to G string. Because G string multiplies this dilaton zero mode, this is equal to the 3-point function of the dilaton zero modes on the sphere. And since this is a 3-point function, the PSL2C is naturally fixed on the right-hand side. So the idea might be to compute the right-hand side first, and then compute Z sphere by integrating that 3 times with respect to G string. these are just some words. I have not put them into practice. I don't know. It should work, especially the one with the disk, where you only need to take one derivative with respect to G string to get a bulk 1-point function. That should be an easier target. So the question that I would like to pose is that, especially for the sphere, what is the simplest background in which the 3-point function of the dilaton zero modes can be computed and will be sort of non-zero and interesting? I think if one can have a nice identifiable target for the sphere, it would be nice, and then I think this procedure could be implemented there. And there were some comments like this also in the Eberhard-Pahl paper. And similar kind of formulas appear in these old ADS papers by Kutasov and Seiberg and so on, where they have an operator they call I, and it's related to the dilaton zero mode and so on. Okay, thanks. Those are all the vague comments I had, and thanks for your attention.
Thanks a lot, Raghu, for the additional comments. And yeah, I wanted to say, like, for the paper you were mentioning from Cetrin, so at some point I was trying to read, and like the prescription is giving to take the derivative with respect to the logarithm of the cutoff. So it's these things which, so I think it's when you write the volume of SL2C and you try to realize, and you get this log of the cutoff, and his prescription is to take the derivative with respect to this to get the finite answer. But I remember that it was giving some weird result because he was claiming that the 0, 1, and 2-point function are proportional to C minus 26, I think.
Yeah.
And so for the 2-point function, it looks very different from what we expect.
Yeah.
So this was, I mean, this prescription was a bit confusing because, yeah, now it doesn't look to match what we computed in other ways.
Yeah. So I would like to say that maybe it's a good point to bring it up that already Harold and Dimitri had a paper with Juan where they explained that how the 2-point function on the sphere is well defined. And the idea is similar, that you have a non-compact family of saddle points, which are related to sort of shifts of the worldsheet time. So you have a 2-point function with the string stretched between those 2 points, and there is a translation symmetry along the string worldsheet. So the remaining gauge symmetry, which is R in that case, it gets canceled by the non-compact family of saddle points. At least that's one way to think about it. But so it seems like in any case, you have this kind of family of saddle points which are acted upon by the gauge group, you can get a well-defined answer. And so, yeah.
No, please.
Well, I was just going to say, it's a good point that you brought up, which I didn't know, that if Cyclin claims that the 2-point function is just 0, that's just manifestly incorrect, right? I mean, the 2-point function is non-zero and finite, gives the normalization of the state.
So I wanted to understand better to be sure that for C equal 26, you don't have some, again, ratio or something happening to give you this delta function. But the way the formula was written in the paper looks like it should be 0. And it doesn't really comment on this. So
yeah, I have a mixed, I don't know this.
And so for this interpretation in terms of like so non-compact dimension and so continuous saddle for the 2-point function, why can't you see the same thing for the sphere partition function? Because like if you imagine Minkowski, you have at least the time and like radial direction which are non-compact.
Right, but what are the saddle points we want to write down?
So it's really like which saddle point we get at the end.
Yeah, the question is, do we have a, sorry. Because for usual flat space string theory, right, we have this action d sigma d tau partial sigma x squared plus partial tau x squared.
Hmm.
It seems hard to come up with the non-trivial saddle points for this, because the equation, well, I don't know, the equation is d sigma squared x plus d tau squared x equal to 0. And the solutions are just x equals constant, right? With zero action. So these are the solutions with the lowest action. And any SL2C map acting on a constant x is just the same x again, right? So
well, what you say that when you have the two punctures, you would get delta function on the right-hand side, and so you have different saddles.
yeah,
It's what you were saying in.
if I remember, I should have reviewed this, but I think the saddles in your case are like x of x depends on the time on this thing. So if we have these 2 points, right, the string needs to stretch between them. So x kind of depends on tau. So that doesn't depend on sigma, but on tau, there is a dependence like tau times x, this little x1, little x2, x2 minus x1, something like that.
I see, okay.
Plus x1. So at tau equal to 0, it's x1, and at tau equals 1, it's x2, right? And there is a, yeah, anyways, I think, yeah, maybe your paper was not presented in this way, but one can present it like this.
Yeah, it's why I'm very happy that you pointed out, because like we're not thinking at it in this way, so it's good to have this different perspective to better understand also the UV and the sphere.
Yeah, so I think they fall in the same category.
Yeah, I really didn't know about this. I was wondering like what's the difference between what's the difference between UV and what we did, and why at the end it seems to work similarly. So I think it's a very good way to see it.
Yes. Yeah. And what the once if you have a sphere and you have 2 punctures, right? The non-compact group is this scaling that moves you up like that on the sphere. And that's precisely here, like translations, I'm forgetting now, but it corresponds to some shift of this saddle point, like this plus a constant or something, or shifting tau by a constant. So it's precisely matches that there's an ambiguity by R, like this amount of rescaling and the shift in the saddle point.
Yeah, cool. Thank you. I think
anyway,
it's very interesting to see it this way. Yes. Thanks. So, do we have other questions for Raghu?
So we considered complex saddles in the level case, right? In this case, do we have to also consider complex saddles?
In principle, yeah. In principle, yes. But the question is, there is also this action here, right? And we want to sum over the things with the least action, and this action is positive.
Yeah.
So
we need to pick a certain subset of complex saddles to make it happen, or like with the
that's a good point. You're saying if you pick a complex saddle which maybe has vanishing action.
Yeah, like certain subset rather. This is like a Witten's latest idea about the what are the allowable saddles are in the 2-dimensional context, I think.
Yeah, that's something relating to the metric, but I guess here what you're saying is if you let x be a complex function, well, this is harmonic, so if x, so this is like saying, dz var of x equal to 0.
Mhm.
So if x was only a function of z, then this would be okay. So if x was holomorphic, then what is this action? If x is holomorphic, is it possible to arrange this action to be 0? Right. So this action, I think, is dzx, dz bar x.
Mhm.
So the action will be 0 if x is holomorphic.
Yeah, but if you consider some
This is
general function, yeah,
well, I think you might be onto something here. So now if x is like f of z, then it satisfies the equations of motion, and this part is 0. So they do have 0 action. Interesting. So there seems to be some infinite family of saddles, just holomorphic functions of x, complex.
yeah. I mean, in general, we can consider f of z plus g of z bar, and that will
That's
that
fine.
will work too. That's what I meant.
Yeah, that's interesting. Well, thanks for the comment. I hadn't thought about this, but kind of like a constant theme in the recent discussions has been every symbol you see in physics, like we're usually used to thinking of it as real, but if you think of it as complex, something new pops up. Yeah, good point. And then if the worldsheet Z was a sphere, is there a way to say that this F should be a SL2C and not more general? What would lead to that? Because right now it seems that you have way more saddles than the SL2C, right? Because F is just some arbitrary function. Like FZ could be any polynomial and it's just fine.
Yeah, I mean, also you can say f is like a not necessarily a function, but changing under PSL2C, right? Like because sigma was in certain sense changing in the Lewis case. So you can consider like some weights K forms or something on the sphere and try to restrict or like cook up a collection of saddles that will make sense.
Yeah, so the question is what makes a saddle good versus bad? So right now we seem to have an infinite number of saddles with this arbitrary function F in it.
Yeah, like even arbitrary forms, it doesn't have to be a function.
Well, X is just a function, right? X, if it's a scalar on the worldsheet, is just in the specific context of the.
Yeah, okay, in this context, that's correct. Yeah, maybe like the way you restricted the saddle in the Lewis case, just like picking the, picking the correct analytic continuation. There might be some prescription to do something similar here.
Yeah, I see. Well, thank you. Thanks for the comment. I'll think about it.
So do we have more questions for Raghu online? Otherwise, I will just stop the recording and we can still chat again a bit for people who want. Okay, it seems we have no more questions, so I'll stop the recording.